In this video, we're going to use the chainrulescore package in Julia in order to define custom adjoint rules which allow us to propagate derivative information over the solution to a nonlinear equation. We can then conveniently use Zygote in order to take derivatives over this expression. Let's get started. Hi and welcome to this new video where we're going to look deep into automatic differentiation in Julia. I'm here in a blank terminal and I will enter the interactive Julia REPL session. For this video we want to solve a nonlinear equation, and the nonlinear equation is usually given in residual form, and here I want to look at the simple example of a residual that depends on a scalar unknown u as well as a parameter theta, and it shall be given as u square minus the sine of theta. So this residual has to be solved by a root finding algorithm to obtain a u that satisfies that, and it is parameterized by theta. So obviously the value of theta will affect the root, and I want to abstract the idea of root finding by using a package called roots. So roots, and then let's create a function I want to call obtain root. So let's say function obtain root, and that shall be a helper function which queries a root finding algorithm based on a certain value of theta. So it returns something, and here I'm using an algorithm from the roots package. It's called find 0. This requires me to hand over the residual function in a format where it only takes one argument. So we are creating a wrapper here which binds the theta parameter to the theta parameter we want to use in this obtain roots here. So that shall be an anonymous function. U maps to residual on u and theta. So basically, whenever the find 0 algorithm queries its main function, that shall be a function that maps from u to something, and theta is always bound to the value of theta. And then we also need to provide an initial guess. And for the simplicity, I will use 1.0 here, since I just don't want to focus too much on the root finding problem, but be advised that this is usually a crucial part, and if this particular point does not converge, then all the subsequent steps we're going to do will also not work. Okay, let's end this function and let me quickly show you how that works. So this obtain root is queried with a certain value. Let's for instance take 1.0 here, and then this gives us the value of the root to this residual equation. And of course you can play around with it. For instance, take 1.5 and get a different root value. The solution to this residual function, or after the root finding algorithm, shall then enter a loss functional. So let's create a loss functional, and I just want to create this in one line. This is a function on u, which shall just be u square. So it's a simple L2 loss against 0. Then we can kind of chain it by saying we want to apply the loss functional to whatever value we got out of this obtain root helper function. So we say loss functional on obtain root, and here let's for instance plug in 1.0, and maybe let's make that more verbose and call it the evaluation point, and plug in here the evaluation point. Here you see that we are first querying the root finding algorithm, and the solution to this is then plugged into a loss functional, and this one gives us a scalar value. And obviously this scalar value depends on the evaluation point. So if I plug in a different point, let's say 1.2, I get a different value. And for optimization or local sensitivity analysis, we might be interested in the derivative of the loss functional with respect to this parameter theta. So we are interested in the dj by d theta. So I just have to write it out here. And how do we obtain that? Well, if you are familiar with automatic differentiation in Julia, your first guess might be just to use any of the automatic differentiation packages available. And a really common choice would be to use Zygote. So let's go for Zygote. I will just write out using Zygote. It takes a little bit to import it. And then Zygote has the handy functionality called gradient, which allows us to perform reverse mode automatic differentiation. Here we now have to create a composite function which evaluates these two functions in a row. So I will say theta is mapped to loss functional on obtain root on theta, and then we have to provide our evaluation point where we want to query the gradient information. So this will now take a couple of seconds. I will just make a cut here. Here we go. That ran for about a minute on my machine here. And we see that we get an error. So quite a long stack trace. And if you go all the way top, you see something like non-differentiable function core.intrinsics.bitcast. So this seems rather abstract, but the general theme here is that one particular step, or probably even more steps, within the chain of functions that are called here is non-differentiable. And exactly here the problem is within the obtain root, and the obtain root calls the find zero function from the roots package. I mean, we don't know exactly what it's doing under the hood, but based on the stack trace, we see that at a certain point it is calling a function or doing something which is just not differentiable. This highlights two issues here. The first issue is that Zygote is trying to go through all these steps downwards to really low-level Julia operations and trying to rewrite them in order to obtain a differentiable path to then get the gradient information. And by doing so, at a certain point, it fails. And on top of that, that is also, even if it worked, it would be rather inefficient because we are then trying to rewrite all the essential steps that are taken here. So what we're trying to do now is to create a hint to Zygote or any other automatic differentiation package in order to not do that and rather use an adjoint problem over the obtaining root solution process, such that we can then call gradient and not do all the digging all the way down into low-level Julia stuff, but rather jump over the solution process by the help of an adjoint. And that works right conveniently by using a package that is called chainrulescore. So I will just clear my screen with Ctrl-L and then import chainrulescore. And this chainrulescore allows us to translate an adjoint rule. And I just quickly want to recap. As you've seen in one of the previous videos where we derived that for nonlinear systems of equations, we can create an adjoint problem for the nonlinear equation. And this one looks as follows. So we will first obtain an adjoint variable. So obtain adjoint variable. And we can do so by saying that a lambda is given as the inverse of the derivative of the residual with respect to u. I don't have the partial derivative signs here, but bear with me. And this one has to be inverted and multiplied with the derivative of the loss functional with respect to u. And then once we have the lambda, we can obtain the loss sensitivities. So this will be step 2 to obtain the loss sensitivities. And here we will get a dj by d theta. So this is what we are interested in. This is basically this local sensitivity, the gradient information. And we can get that by saying minus lambda multiplied with the derivative of the residual with respect to theta. And the way we're going to implement that is to be a little bit more general, because this particular information, dj by du, could also be coming from a longer chain. So what we're going to implement now is something that might be valid for even longer compositions, not just this small composition with obtaining a root and then plugging it into a loss functional. Okay, but how does that work? And for this, we're going to implement a function which has a certain signature, and then Zygote will understand the shortcut. For this, let me clear the screen, and then we can create a function which shall be from chainrulescore.reversRule. This function shall have the signature that it takes as argument a function type that is similar to the obtain root. So we will say that the first argument is something that is of type obtain root. And then as the second argument, we have the actual argument to the function. And this one here will be the theta parameter value. And since Julia is a multiple dispatch language, that means that these reverse rules that we are writing here is a collection of a bunch of rules that already exist and Zygote or other automatic differentiation packages are using in the background. So we're just adding another one to the library. And this reverse rule requires us to return first the primal solution, which can also be called the classical solution, as well as a pullback function. Let's first compute the classical solution. We can compute that obviously by taking the parameter theta at which we want to evaluate this reverse rule and calling the obtain root function on it. And this is also a theme that you see in adjoint methods, that whenever you want to use them, you first have to solve the actual problem. So in our case, this is solving the nonlinear equation. Then we also define a local function, which I want to call obtain root pullback. And that is this aforementioned pullback function. And you can think of it as something that goes in an opposite order than the actual obtaining root. Obtaining root is a function that maps from theta to u, but this pullback shall now take a tangent of u and map it to a tangent of theta. So this is a function which takes a u tangent, and this is this derivative information I meant earlier. If we have a longer chain, this is the information that is coming from points further down in the chain. In our particular case, this will just be the dj by du, but as said, it could also be deeper. Well, what does this obtain root pullback do now? So essentially what we're doing is to evaluate that expression here by first computing our adjoint variable using the inverse to this derivative information, multiplying it with the tangent we get, and then create the dj by d theta by just evaluating this. And in order to do that, we need additional derivative information. So we need the residual with respect to u, as well as the residual with respect to theta. And there are now a couple of options. So one option would be to do that with a handwritten derivative. If you recall, the residual function is rather easy, so we are easily able to do that. The other option is to use automatic differentiation on that. And that shouldn't be problematic because this is just an explicit forward computing function, the residual, and there is no implicit problem involved, like the solution to a nonlinear equation. Although it could also be the case as long as it is correctly chained. A third option would be to also use a pullback, which is a little bit more advanced, and you will see that in one of the future videos. But now let's use Zygote in order to obtain this derivative information. So we're going to get the del r for the residual with respect to u, as well as the del r del theta, by calling the gradient function from the Zygote package on the residual function, and maybe let's go to the next line, on the residual function, and this shall be evaluated at u classical as well as the theta value that we want to have the derivative at. And here you see again that in order to have a correct pullback, we again need a classical solution from this forward pass. Well, then we can first obtain the adjoint variable, so the lambda to say, and for this we will do 1 divided by del r del u multiplied with u tangent, so the tangent information. And here also a quick reminder that this particular way of inverting of course only works in a scalar case. If that was a Jacobian matrix, which you would have if you solve problems over nonlinear systems of equations, you would have to use a linear solver, so an LU decomposition or a conjugate gradient algorithm. And there are also some considerations that the one might have to do there. And then we can use the adjoint variable in order to propagate the tangent information. So here it's called dj by d theta, but in essence this is just an theta tangent. So this will be theta tangent. And in order to get that, we have minus adjoint variable multiplied with del r by del theta. And now it might be tempting to return this theta tangent as part of this local obtain root pullback function. However, in order to have the correct pullback, we also need to provide a tangent information to the function, which is a bit abstract, but luckily for us, this is just a no tangent, and there is an object implemented in the chain rules core in order to translate that. So let's call that the obtain root tangent, and this is just a no tangent, opening closing brackets. Then this local function returns the tangents in the same order as the arguments to the reverse rule. So first we have the obtain root tangent, which was just the no tangent, as well as the theta tangent information. Then we close down our local function. And as part of the bigger function, the reverse rule, we will now return the uClassical, which is the classical forward evaluation of the function we want to create an adjoint rule for, as well as our pullback function that we just created. So obtain root pullback. And then let's have an end here. Here we go. Now we have that implemented. Let's now try again to use the gradient function from Zygote on our chain. So this is the one we had before. And let's run it again. And we see, oh no, it still raises an error. And that's not because we made a mistake in this adjoint rule implementation, but this is rather because Zygote is not yet aware of that rule. And since we are in this Julia REPL session, what we have to do is we have to exit the session. So I hit Control D and then enter a new one. And now we have to repeat a couple of operations. Let me first clear the screen. Let's define the residual again. Then import the roots package, then create our function obtain root again. So I'm just using the arrows up in order to get what I had in my command history. Then let's define our evaluation point, define the loss functional, exactly. And then let's import chain rules core. And now I want to type out the beginning of the adjoint rule that we just created. So this one here using my arrows upwards, and I'm getting what we wrote in the previous session. I hit enter to execute that, and then I can import Zygote, and now Zygote should be aware of the adjoint rule that we implemented. So let's try that out, use gradient again, and let's see if it works. So again, it takes some time in order to compile that on the fly. It should be a bit faster than the previous one where we had the stack trace, because here Zygote shouldn't be like digging all the way down. And here we go, fantastic, right? So now we have a gradient information. So this is the derivative of dj by d theta. Now you might argue, well, this is just a number. I mean, at least it works, but is it also correct? So let's check that with finite differences. So check the derivative with finite differences. For this, let's define step length. So let's define a step length, and I just use 1.0 times 10 to the minus 6. And let's compute the finite difference derivative. And I will just use that over multiple lines. So we have first to evaluate our loss functional at obtain root at the evaluation point plus the step length. And then we are subtracting the loss functional at the obtain root at the evaluation point. And then we have a closing bracket, and we will divide by the step length. And here we go. This is the derivative according to finite differences. And we see that it is identical to the one that is found by Zygote up to, well, about the 5th digit after the comma. And that is of course to be expected, since the finite difference derivative has a considerable amount of floating point routing error. So there's a good chance that the derivative we obtained by automatic differentiation together with the adjoint rule is more precise. That's the end of the video. I hope you enjoyed this custom implementation for Julia in order to provide the automatic differentiation tools there with hints how to propagate derivative information over arbitrary expressions. And this is helpful not just for these really simplistic examples, but for instance, if you implement something complicated yourself in Julia, or something where you call a third-party library, things that might either be hard to differentiate with Zygote or even impossible in case you call external libraries. And then you have to kind of implement that yourself. And although it might be a little bit intimidating at first, it's actually quite elegant to do so. And once we have a collection of really good chain rules or adjoint rules, automatic differentiation becomes so much more useful in Julia, because the packages are aware of these hints or shortcuts how to efficiently take derivatives. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. And here you will now see similar videos. I hope to see you in one of the next videos.